But right now, I am so pleased to introduce tonight's presenter. Alex Trunnell is an astronomer and educator based in Somerville. Alex has done planetary science research with Vassar College, MIT, and the Lowell Observatory. And her passion is bringing this research to the public through astronomy outreach. She is especially interested in exoplanets and life in the universe, and she is an amateur astrophotographer. Welcome, Alex.
Thank you so much, Lily, for that warm welcome. That was lovely. It's so great to see you all tonight. Thank you so much for coming out, especially on a holiday week. I'm so impressed with this turnout, and I'm so excited to spend some time talking about astronomy with all of you. As Lily said, my name is Alex. I am an astronomer and an educator based in Somerville, but I do lots of outreach at different libraries around the Boston area. Ooh, please hold. There we go. I went to Vassar College for my undergraduate degree and studied physics and astronomy there and was a double major, so have a background in sort of the practical science of astrophysics. Then went on, came to Boston in 2017, got my Master's of Education at a partner institution of MIT called the Woodrow Wilson Academy. While I was doing that, I kept doing my astronomy work. I was a project assistant for MIT. That work took me down to the Lowell Observatory, in Flagstaff, Arizona. And all of the work I've done has focused on solar systems, asteroids in our solar systems. The work I did with Lowell Observatory was about Jupiter's moon Europa. And the work I did in undergraduate as my senior thesis were all around other solar systems, looking at exoplanets around other planets, around other stars. My background is also in education. As Ali mentioned, I have been a full-time teacher. I spent 4 years as a math, science, and technology teacher teaching physics, calculus, and observational astronomy at a school called Meridian Academy in JP. And I currently work as an instructional designer, taking my education skills and applying them to lessons for all folks. Today I'm going to be talking to you all about the gas giants in our solar system, Jupiter and Saturn. We're going to start by talking about our solar system more broadly, the formation of the planets and what exactly a planet is. Then we'll look a little bit more specifically at each Jupiter and Saturn. We're going to talk about their features, and we're going to talk about the missions we've taken to those planets and what that told us about these gas giants. First things first, what is a planet? And this is not a rhetorical question. If anyone has an idea, I'd love to hear it. What do you think a planet is? I'm a teacher, as I already said. That will become very clear about this. What's a planet? Any takers? Yeah.
I thought a planet is orbiting around our sun in our solar system.
Excellent. A planet is orbiting around our sun in our solar system. You're most of the way there, yeah. A planet, very specifically, was redefined in 2006 to be a little bit more specific than something going around our sun, because there's lots of stuff in orbit around our sun. If anyone recognizes the year, 2006 is the demotion of our dear Pluto. So this is the ruling that made Pluto a dwarf planet and not a planet. And the reason for this is we started finding bodies in the solar system that were a lot like Pluto, not too much like other planets, and we realized either Pluto was going to have to be reclassified, or we're going to end up with dozens and dozens and dozens of new planets. So we looked at what makes a planet, we looked at what makes Pluto different, and the International Astronomical Union, the governing astronomy body in the world, came up with this new, updated definition of planethood. You have to meet 3 specific conditions to be a planet. 1, you have to be in orbit around the sun. So something like the TRAPPIST system, a very famous exoplanet system, is an exoplanet, not a planet, because it orbits a different sun. So to be a true planet, you have to be in our system.
What is an exoplanet?
Great question. A planet around a different star.
Got it.
You also have to be molded by your own gravity into a round or nearly round shape. This is an image of the asteroid Vesta. As you can see, it is not quite round. It's almost round, but it's sort of a lumpy potato shape. And anything that is lumpy potato shaped is not a planet. Instead, it's something like an asteroid. And finally, and this is the one that got Pluto, you must have cleared the neighborhood out around your orbit. A good example of this is something like the planet Jupiter. We'll be talking a lot about Jupiter tonight. Jupiter is what we call the governing body in its orbit. It's very close to the asteroid belt, it's got a lot of moons, there's a lot of stuff going on near it, but Jupiter is in charge. Everything around it revolves within Jupiter's grasp, and Jupiter is what we call gravitationally dominant. Pluto, not so much. Even its own moon is yanking it around back and forth, and there's lots of other stuff in the Kuiper belt. That's where Pluto is. You can see in this image, this belt of Pluto-like objects here. All of those are not clearing out the path. We don't have anyone who's gravitationally dominant, and because of that, Pluto is considered a dwarf planet. One more thing I'll add, Pluto also has a very inclined orbit. Most of the planets are like this on a tabletop. This is foreshadowing. We'll talk about why that is in a few minutes. Pluto is tilted. It's up like this. So 3 things need to be a planet, and tonight we're going to be talking about 2 definitely, absolutely planets, probably the 2 most defined planets in our solar system, Jupiter and Saturn. So how are planets formed? Well, generally, when a star is formed, you have a cloud of gas and dust called the interstellar medium, between stellar stars. You have this gas, this dust, these molecules that exist in space in between where systems of stars are. Typically, this cloud is gravitationally perturbed. Something happens that begins to cause a collapse. This can happen in many ways. Sometimes it's just the result of the natural motion inside the cloud itself. Sometimes it's an external force. We think one of the most common is colliding black holes. 2 black holes collide together, create a larger black hole, and the gravitational waves, which we have observed, we know they're real, cause ripples in these clouds that cause them to condense and collapse. And when matter collapses, you have molecules hitting molecules, atoms hitting atoms, and you begin to form sort of bigger molecules and atoms, and then bigger masses until you have all of this stuff that is all being drawn toward the same central location, and you collapse with a massive amount of energy, and you form a star. Now, when that happens, you have stuff left over. A lot of the central stuff becomes the star, most of the hydrogen and the helium, some other of these elements that are very abundant out in the ISM. But all of this leftover stuff has to go somewhere, and where it goes is into the formation of planets. Now, also during this process, we go from having a cloud of stuff to having a disk of stuff. Essentially what happens is everything is in motion, and over time, as that stuff has different kinds of motion and starts collapsing and colliding, all of that motion starts going in the same direction.
How long does this take? How many
millions and millions of years, billions of years. It's a very slow process. Great question.
Yeah.
So we're talking very long stretches of time. What happens with your sort of spherical cloud of stuff is it starts spinning, and it spins faster and faster and faster, and as it spins faster and faster and faster, it starts to flatten like a pancake. So now all of your stuff is in the same plane. Then you have the same kind of snowballing process of stuff sticking to other stuff, forming bigger chunks. Then that is gravitationally dominant and starts pulling stuff together. So you have a cloud that flattens and then starts to sort of carve out these areas where you have bigger chunks of rock or gas or ice. And that's what forms the seeds of our planets as they start getting more and more of that stuff that comes toward them. These planets then remain in orbit around that star, using that same motion in that same direction they had when they were formed. Yeah?
So that pancake that you just talked
Yes.
about, is always in the same angle, or it's just...
Great question. All of the planets are in the same angle of the pancake, but our systems could be in any direction. Great question. When we look at systems outside of our own solar system, we have what we call an observational bias, the ones we see more frequently. And a big observational bias we have is for systems that we can see sort of flat side on. So instead of like this, if we see them like this, we can actually learn more about those systems. So they do vary. We tend to look at the ones that are sort of in our plane. So I just gave you all a bunch of information about a process that I said took hundreds of millions, if not billions of years. How could we possibly know that that's what happens?
Yeah.
It's not like we've seen it happen. Humans haven't been around that long. So how have we figured this out? Or how do we have this good guess? Well, we've seen what we believe are sort of middle of the process systems. This is an actual image. Some of these are computer simulations, but several of these are real images, including HL right here. These are what we call protoplanetary disks, or proclids. These are those disks around central stars, you can see our star here, that are in the process of becoming planets. And it's only very recently that we've started to actually see these. And this was what did a lot of work for us in sort of figuring out what we see when we see these systems. And new observations are being made literally every day to improve our understanding of the solar system. So even though we have a pretty decent sense that this is what's happening, every day our model gets a little bit better. This was something that had a lot of unknowns about it a decade or 2 decades ago, and we're really starting to solidify what we know because of these direct observations. However, no model we have is quite perfect yet. We've seen that our solar system, which is very neat and tidy and has rocky planets and then gas giants and ice giants and a nice row, not every system is like that. So while we have a really good idea of the foundation of planetary formation, we still have a lot of question marks about what exactly happens at the fine-grained detail level in terms of how we end up with some weird situations. If anyone's ever heard the phrase hot Jupiter, sort of a nice buzzword, these are giant Jupiter-sized planets that end up very close to their star, like closer than Mercury is to our sun. So they are very hot, they have very fast orbits, and we don't have one, so we don't know how they get there. So this is a very interesting, ever-changing field of science, but we do feel pretty good about the foundation we have.
A question?
Yeah.
What's the difference between the planetary disks that are hollow in the center versus the star center?
Good question. So these in particular, I think this one might be a black hole system, if I'm not mistaken. Sometimes when you have those collapses, you can have a like truly massive collapse. And we have seen some systems where the center of the system is not an active star. Could be something like a brown dwarf, which does not sort of luminesce in the same way. We have lots of different sort of options for what could be at the center of the system. Great question. We can also see sort of a difference in, you see how the lines here are thicker than here? So we're seeing a difference in what has been sort of scraped into planets already.
So is that considered like HL and TW a solar system versus HD 1P whatever is like called something else because it's not solar in the center?
Yeah, great question. Yeah, so these are solar systems or proto-solar systems. This guy, I'm looking at it, it's a very interesting shape as well. It's almost like a galactic shape. It might even be a proto-galaxy. Just looking at sort of what's going on with the way things are forming. Great question.
I'm not exactly sure how to describe it, but how many light years are they away from us?
Oh, great question. So the closest star to us, Proxima Centauri, is 4 light years away. These are much further. Sometimes thousands, sometimes tens of thousands, sometimes millions. There's sort of a direct relationship to how bright something is and how far it is. So if it's brighter, we can see it if it's further. If it is dimmer, we can only see if it's closer to us. So there's no direct correlation between sort of what you're seeing and how far away it is.
So how do we even see it?
Great question. Really good telescopes. And we have instrumentation. James Webb Space Telescope is a great example. James Webb is far away from Earth. It is about 1 million miles away, which means it is far away from our atmosphere and rain and clouds and has a crystal clear, picture perfect view, and is also massive, like the size of a room. So it's got a huge mirror, which means it can gather more light, and it's got a clear view. So we can actually see quite a bit when you remove those variables, especially for stuff that's brighter.
So I don't understand, did we send that into space?
Yes, yeah. So telescope on a rocket, and then we sent it away, and there's a very cool process of basically unfolding the whole telescope that we sent in like a small payload.
Wow.
It's very cool, yeah. You can find simulations of it online, it's really cool. Great question. So we have our disk, and we end up, as I alluded to before, with a very clear-cut vision of our planets. We have rocky planets, then we have our gas giants, then we have our icy planets. And this isn't a mistake. This is actually something that happens in that formation process. Protoplanetary disks contain both gas and dust, and often some ices as well. And ices can also form later down the road. What happens is that gases cannot condense within about 4 astronomical units, and an AU is 1 Earth-Sun distance. So if you are 4 times as far away from the Earth, that is your cutoff for where you can form gas planets. Because it's too hot, the gas won't condense. It will stay in its active state, and it will not be able to sort of come together and form planets the way it needs to. Jupiter is 5 astronomical units away from the sun, so it is safely past that mark. So it was able to condense. The other issue we have is what's called solar wind, which essentially is solar particles coming off the sun. These very lightweight elements, like hydrogen and helium, can get blown away very easily by the solar wind, which essentially blows them back into these outer regions of the solar system. In a similar way, our icy planetesimals being small planet-like things, anything icy is not going to form in front of what we call the snow line. This is where those elements will melt because they are too close to the sun. However, they can form in these sort of outer regions of the solar system. So as you have your gas giants forming with all of that blown away hydrogen and helium, you have your ice giants forming out of the icy stuff. The gas giants tend to get most of that hydrogen and helium. Anything that gets blown away is absorbed by those gas giants before it has a chance to make it out to our icy planets. So we tend to see our ice planets are a little bit smaller. And we see that in our own system. So speaking of smaller, let's take a peek at our solar system and compare the planets that we have to all of that theory we just set up. So here are the planets and Pluto by size. So all of our relative sizes are correct. You can see the sun is so big we barely get a sliver of it. The sun is massive. About 1.2 million Earths could fit inside the sun. It is absolutely enormous. We have Mercury over here, very small rocky planet. Venus is about 97% Earth size, so it is nearly identical to us. Venus is often called Earth's evil twin, because it was almost identical to Earth. It was just a little bit too close to the sun to sustain habitable life, and instead its atmosphere had a runaway greenhouse gas effect, and it now has a massive carbon dioxide atmosphere that covers the whole planet and has things like acid rain and massive pressures and extremely high temperatures. But by size, very close to Earth. Mars is about a third of the size of the Earth. Much smaller. Some folks think that Mars is actually inside a zone where we could have life, but it's so small it couldn't hold on to its atmosphere, which is why Mars has no atmosphere and is today rocky and barren. And then you can see here, superimposing, here are the giants, Jupiter and Saturn. To scale with our planets, they are just massive. At times, this is the great red spot on Jupiter, which does fluctuate and change. It's actually getting smaller now. There have been times when this great red storm is bigger than the Earth itself. They are massive. Even Saturn without its ring is still massive. Tons and tons and tons of stuff inside these planets.
How do you measure one?
Good question. We've sent probes. We'll talk about that. We can also learn a lot about these planets based on how they orbit and how other planets behave around them. We actually found Uranus and Neptune over here because of how they perturbed, how they messed with the orbits of Jupiter and Saturn. So we can actually see the effect, and we can basically calculate how far away are they based on how quickly they're moving across the night sky. That's a relatively easy calculation with Kepler's laws. Using that, we can figure out how far away they are from, in this case, Saturn. We're talking about Uranus. And then we can figure out, okay, it's this far away from Saturn, and it's messing with its orbit this much, so we can infer it must be this size. Because we can do experiments on Earth about how gravity works.
What is the Earth?
Great question. What was your question?
Earth.
Earth is right here.
It's Earth. Okay.
Very small in comparison. Yes, question.
Will any of those disks ever become part of our solar system, or are they part of other systems?
Good question.
When
So,
they develop into planets?
great question. The disks I showed earlier are all in different systems. Most of them are very, very far away. And because these things take so long, they will look almost exactly the same for probably the entirety of humanity. So what we actually do is we look at different disks in different systems at different stages to try and put together a picture of what we think is actually happening, like a timeline. So if we took a timeline and chopped it up and scattered it through the universe, we're trying to put those pieces back together. So all different systems, all over the place, trying to use them to put the story together. Great question.
I have a philosophical question, because I always wondered about it when I was a kid. Do we have any idea where the end is? Is it infinity? What is that?
So this is a great question. We think that we're sure that the universe has no edge. We can sort of map what we think the universe might look like, and we think it is some version of basically like a big torus, like a donut kind of shape, all of which is to say, we're not positive.
We don't know.
Physically, where is the end? There isn't one, which I know is very unsatisfying. In terms of what the end of the universe looks like, there is the dramatic version and there is the more probable version. The dramatic version is that a long time ago, 13.8 billion years ago, there was a big bang and everything expanded outward, and we are still expanding. And there's this huge expansion that's happening everywhere in the universe, like a balloon being blown up. The big crunch, as they call it, is the idea that that expansion can only go so far. We will run out of energy, and if you blow up a balloon and then you stop blowing it up, all of the air disappears. It all comes out the side of the balloon. So the dramatic version is that maybe the balloon will stop being filled and will crunch back together. In my opinion, the more probable version is that there's a finite amount of hydrogen. What happens when a star burns, when we have light from a star, is it's taking raw hydrogen and it is converting it into helium, and then it's converting that helium into other elements, so on and so forth, and that's creating heat and light from those chemical reactions. And that's great, and that's what gives us light and warmth and life, but hydrogen is a finite resource. We can't really make more in the universe, even if we can in the lab on Earth, we can't in the universe. So eventually we'll run out of hydrogen, and stars won't be able to shine anymore because they'll be out of fuel. So very, very long from now, what will probably happen is that the universe will just go dark. And if there's no light, there's no life, which is very sad.
I liked when you said donut, because that sounds as
It
if
sounds a lot
we'll just
nicer,
keep
right?
going.
Yes, yeah. The thought question of what happens if you reach the end of the universe, people have written whole novels on. Like, it's a really interesting question. It's a great question. Yeah, do you have a question, Becker?
When you were talking about hot Jupiters, would those be still gas giants, or would those be rocky planets?
Good question. They're still gas giants. We think that they migrated. So we think that they formed out here, like with Jupiter and Saturn, and then over time moved inward toward their suns, because we are pretty darn sure that you can't form that close to a sun if you're made of hydrogen. Good question. Yeah.
Do they think that Jupiter is a star that just didn't make it, or that just doesn't have enough gas pressure, to turn into a star, so it stayed a planet?
Great question. I believe Jupiter is safely out of the realm of failed star. There is sort of a cutoff. Like, if you have enough hydrogen and helium, you will just become a star. We're pretty sure that Jupiter is relatively far away from that. We have seen some instances of bigger Jupiter-ish planets, like 25 Jupiter masses and so on, that are much closer, and some even start to blur the line of, are they doing some of the star things? Are they actually having some solar reactions? Maybe. So this is also a very interesting field of science. The more data we get, and Kepler is a great example, the Kepler Space Telescope spent the last about 2 years of its mission just taking data constantly, just looking at a patch of the sky every night over and over and over again, getting us millions and billions of stars that we could look at. So this is a great example of stuff we are finding out and learning more about every day. Good question. I'm gonna take one more and then I'll move on. Yeah.
Is there life on any of these?
Great question.
What kind
Only
of
this one. We are fairly confident, very confident, that there is no existing life in our solar system other than on Earth. It's
As we know it.
possible, sorry?
As we know it, it exists like
Yes.
that.
So
Could be some
it's
other-
possible there might have been life on, for example, Mars. And like I mentioned earlier, we think Mars had an atmosphere, it was just too small and lost it over time. It's possible that maybe there was something during its atmosphere time. It's also possible maybe there's life that just looks different. We have a very sort of narrow definition of life. It's made of carbon, it needs oxygen and water and light, all of these sort of things. That kind of life we don't think can really be anywhere. Maybe on some moons. Maybe, if we get really lucky and conditions are perfect. Maybe on some moons. Definitely not on these planets.
All right, but if you have airplanes, people, pilots, American pilots, who say they're flying and all of a sudden they see weird things also flying in the sky.
I definitely don't think there are aliens here. I think we know. That's this is not really a science thing, this is just a personal thing. I feel like if there were aliens, we'd know.
No little green men.
So here
take
is
a
a
step
similar
forward.
chart, but instead of size, this is distance, to give you a sense of scale. Our entire inner solar system is a very small portion of our solar system as a whole.
Look at these.
The distance between, let's say, Earth and Mars is nothing
Yes.
compared to the distance between Earth and Jupiter,
Too much.
or Jupiter and Saturn.
How did
This
we
is a
know
good,
that
this is the reason that Mars is such a hot topic, is it's very close in the grand scheme of the universe. The moon is very close, Mars is very close. We can get to the moon in about 3 days, that's nothing. We can get to Mars in 8 months or so if we time it right, which is hard, but you can do it, we could do it. Something like Jupiter or Saturn, this is travel time. It takes light 45 minutes to get to Jupiter and an hour and a half to get to Saturn. So it would take us, humans, traveling at much, much less than the speed of light forever to get there, especially if we're doing it in a way that is sort of safe for humans and humankind.
That would be good.
Yeah.
I was just wondering, are we pretty sure that all the planets are within only a few degrees of the ecliptic plane?
Great question. Yeah, I mentioned earlier that Pluto has like a pretty wide, it's pretty tilted. All the other planets are within somewhere in the neighborhood of like 0 to 4 degrees of like a perpendicular. So everything's very close. Pluto is more like, I think it's like 18 degrees. So it's got quite a bit more tilt to it. But yeah, for the most part, these are all pretty much in a line. Remember that in 3D space, they're very rarely going to be lined up like this. They'll be in sort of different places in their orbits. But this sort of distance scale is really interesting. One other thing that I'll mention is these distances are very sort of nice and neat. AU, that's our astronomical unit, our Earth-Sun distance. We look at AU, Earth is 1 distance, Earth distance to the Sun. Jupiter is about 5, Saturn's about 10, Uranus is about 20, Neptune 30, and the Kuiper Belt 40. Those are very round numbers, and we think that is a coincidence.
What'd you call the last one?
Kuiper Belt.
The Kuiper Belt, yeah, that's where the Pluto stuff is, kind of all out here. So, let's talk about our planets of the hour, Jupiter and Saturn. And these are the planets that hopefully, clouds willing, we'll be able to take a look at through our telescopes in just a few minutes. So, Jupiter. Let's run through some fun facts about Jupiter. It is, as I mentioned, 5 astronomical units, Earth distances away from the Sun, so it's 5 times further away. Its year, the time it takes to complete 1 orbit around the Sun, is equal to just about 12 Earth years, 11.86.
Wow.
Jupiter is named for the king of the gods. It is the biggest planet in the night sky. Venus is a little bit brighter because it's so close to us and has all those shiny clouds. But Jupiter, even the ancients knew, was more massive.
What's
so it is
the
the king of the gods.
The orange button on it.
This is a storm. Good question. We'll talk about that soon.
Who named Jupiter? Who named?
Good question. Our naming conventions for the planets are typically based off of ancient mythology and are often carryovers from sort of just through Western civilization. Uranus and Neptune and Pluto we can sort of pin because those were named in the last few hundred years. Uranus and Neptune were named essentially by the folks who found them in their various scientific groups they were part of. Pluto, I believe, was named by like an 8-year-old girl as part of a contest. So those more modern names we can pin a little bit. At last count, and this is a number that has been increasing steadily since Galileo first saw Jupiter through a telescope and saw 4 moons. Right now, our current moon count on Jupiter is 95. Most of these are invisible with the telescope here on Earth. Many of them you can only see with space telescopes or with flybys of the actual planet. That is foreshadowing. Jupiter was known to the ancients, as was Saturn. I mentioned earlier that Uranus, Neptune, and Pluto and other Kuiper belt objects were not. Those we can't see without a telescope, but Jupiter and Saturn are totally visible to the naked eye, especially if you didn't have light pollution. So some fun facts about Jupiter. It rotates every 10 hours, so even though its year is much longer than ours, its day is shorter. And it is primarily made out of hydrogen and helium, just like our sun. So as we mentioned, all those gases got blown down into that belt where our gas giants are. Most of our gas giants are just hydrogen and helium, left over from our star production. Yeah.
It rotates every 10 hours. Do the different layers rotate at different speeds with all the gas?
Good question. So the planet itself as a whole rotates every 10 hours. In addition to that, the storms have some movement as well. Not quite as quickly, but there is some movement to them. So this is the composition of Jupiter to give you a sense. About 75% of it is hydrogen and 24% is helium. So less than 1% of the planet is stuff that isn't hydrogen or helium. Now it is in different forms. We have metallic and liquid hydrogen here, for example. That's due to the pressure because of the mass of the planet. So all of that pressure on the hydrogen and on the helium as well forms these layers.
How did you discover that?
So we've set probes, and that's actually a great segue into the Juno mission. We know a lot about these planets because we have studied them extensively. We can do things like use spectrographs. This is what we do when we look at the kind of light we get coming off the planet. I did some work to this effect on Jupiter's moon Europa when I was at Lowell, and that is something that is a very effective way to figure out what a planet is made of. And that's an interesting way to find out what's on the surface. So that's how we know that on the surface of Jupiter,
Oh, pretty.
we have these clouds. And that can tell us that most of these clouds are other stuff. Our ammonia, our methane, our water. We have storms on the surface, so we can figure that out. But we also have these probes, like Juno, that conduct flybys, and sometimes, in the case of other planets, can even go deeper than that. Juno was a mission launched on August 5th, 2011, and it took 5 years to get to Jupiter. So we got there on July 5th, 2016, and the mission is actually still in use. It was originally planned to wrap up a few years ago, but as is the case with many of these missions, the instrumentation was so meticulously crafted that it has worked long past its initial expiration date. It's actually still in use. The most recent extension puts it through to the end of 2025. So Juno is still going strong, still bringing us back data. And there's a ton of instrumentation on board this spacecraft. So we're looking into the planet, we're looking at the clouds, we're taking spectra, we're doing all of these different things with all of these different instruments to really figure out what's going on with Jupiter. In terms of Juno's name comes from Greek and Roman mythology. The god Jupiter drew a veil of clouds around himself to hide his mischief, and Juno, his wife, was able to peer through the clouds and reveal Jupiter's true nature. So this is a quote from NASA on the naming of the probe. The goal here, of course, being to learn more about this planet, to peel back those clouds, to figure out what's going on under the surface. The nice thing about Juno is it's a relatively recent mission, and the last 20 or so years have been enormous in scientific progress. They've been especially enormous in photography. Our cameras that we have now are phenomenal. So Juno is very well known not only for its great scientific work, but for the absolutely stunning imagery it has produced. Not only has it produced excellent images, Juno has done something that's also groundbreaking, which is to essentially say, we have thousands, hundreds of thousands of images. How can we process all of them and learn as much as we can? So this is actually a citizen science effort. There are people who have learned the skills of astrophotography and learned the skills of photo processing, photographers, amateur astronomers, scientists, and they're able to access this data and do their own analysis. And sort of, it's really a team effort, which is really exciting. So we've got some really, really stunning images. We are getting very close to the planet. Juno is in a very close orbit. It's getting extremely clear imagery. We're seeing Jupiter's south pole and some of these little storms here that form in their own little regions. Some of these swirl storms on the pole itself. And we're seeing that the pole has a very different makeup. It's made of different stuff. Because images have been processed to bring out that contrast. A lot of the ways that this kind of image is processed revolves around looking at what kind of elements there are. So in this case, the blue is indicating a different material or a different substance than the surrounding. So you can see that we have a real sort of collection of material on the poles, and we can get a really clear idea of what these storms actually look like, and these sort of swirl patterns that make up the whole planet and really define it. Here's another view of some of the storms on Jupiter. You have many storms similar to the red spot, where you have these circle storms form. Basically what happens, the layers of Jupiter, it looks very layered when we look at it. We should be able to see that through the telescope tonight. You have layers one on top of the other, and the storms move in different directions. So this storm might move this way, the storm on top of it moves this way. So when you have these two storm fronts going in opposite directions, where they meet, the material can get tangled together. It can sort of overlap and get tangled, and that's what forms those circle storms, those balls. So we can see that we have a bunch of those, particularly where our layers meet. You can see here this layer and this layer meet and form these circle storms. And here's another look at a band of storms on Jupiter. And it's really that beautiful, beautiful photography we got from Juno. So Saturn, also a gas giant, very different. We are very lucky that in our solar system, we have two radically different planets of the same classification like this. So you can see Saturn, of course, has its beautiful rings. It is 10 astronomical units away from the sun, so twice the distance of Jupiter. The length of its year is about 30 Earth years, so even longer to go all the way around the sun. Saturn is named for the Titan father of Jupiter, because it is sort of further out, sort of looking over Jupiter, if you will. And Saturn tops Jupiter. It has 146 moons at our last count. Many of these are actually inside of the rings. So the rings of Saturn are actually, over time, forming small moons. So every time we sort of see a new one, it gets added to the count. So this count includes those ring moons, which is why it's such a high number. Yes?
Is there any plan to send something like the Cassini probe, back through, the rings, or do we get enough data from Cassini?
Can you ask your question again? I don't think I heard you.
Do we get enough data from Cassini about the division, or are there any plans to send other probes through the ring system?
Good question. So the question was about the division in the rings, and if the probe we sent back in the 90s, we'll talk about that shortly, was able to get us enough data. Yes and no. I mentioned earlier that there is just an explosion of technology in the last 20, 30 years. I think this is very clear if you look at the differences in something like Mars rovers. We've been sending those pretty consistently in the last 30 to 40 years, and the quality is just like skyrocketed. So there's a lot of interest in sort of renewing these missions that were, at this point, relatively outdated. So I believe on the current docket, where I want to say 2027, is sort of a Saturn mission with a lot of focus on the moon Titan. I believe it has not been approved. So TBD. It has been approved. I've been told it has been approved. Thank you for clarification. Yeah.
Who approves it?
Good question, NASA. A lot of times just sort of the government budget at large. There is every 10 years, a group of astronomers come together and form what they call the decadal survey, which essentially ranks the priority of astronomical missions for the next 10 years.
And what causes the rings? Why would there be, since they're in relatively close proximity, why would Pluto not have rings as opposed to Saturn if they're both comprised of the same gas?
Good question. We think it's because of the way it formed, that there was excess material left over that formed into this ring structure. Many planets actually have some form of ring. Uranus is a great example. Uranus we actually know is sort of tipped over, so it has a ring going this way. Many of these rings, Jupiter has a ring. They're just very small and not quite as noticeable. So the effect of excess material forming a ring is not uncommon in planets of this size. Saturn's just happens to be especially pronounced. Great question. So Saturn was also known to the ancients. It's also visible to the naked eye and visible through rudimentary telescopes. Earliest drawings of Saturn actually have sort of 3 circles. It wasn't until Galileo's 3rd or 4th iteration of his telescope that he was able to make out the ring structure. Some facts about Saturn. It is also made of mostly hydrogen and helium with some ices on the inside. But Saturn is different from Jupiter in that it has such a low density that it is actually less dense than water, which means if you could put Saturn into a bathtub, it would float.
Oh,
So it has a lot of material, but it's much more spread out than something like Jupiter. Very low density. You can see here a lot of similar effects. We have our metallic hydrogen and helium. We have our liquid hydrogen here. A lot of the layering is very similar to on Jupiter. But we also have, of course, our rings. The way we name the rings is we have sort of your major rings are numbered, starting with A, then to B, and so on. And our divisions are typically named after famous scientists. So we have sort of that naming system using our letters and our modern scientists.
Well, wait, I've got a question. Could you go back to that? So, there's a division between, there's a space between ring A and ring B, and then there's the naming of things. What's the difference in the A rings and the B rings? And
Good question. It's a helpful naming for when we look at things like the makeup of those rings. The rings of Saturn are extremely varied. Some of the particles are the size of like a grain of sand. Some are more like a minivan in size. There's a lot of variety going on. The divisions themselves are often where moons have started to form and cleared out a path for themselves. So having this naming scheme is helpful when we think about what's different, for example, about the B ring to the A ring, because there are some differences. Great question. Our Saturn mission is a little bit more outdated, hence the mission I mentioned earlier that's going back with modern instrumentation to gather more data. The Cassini-Huygens mission was launched on October 15th, 1997, and it took even longer to get to Saturn's orbit, on July 1st, 2004. And it had what we called its grand finale in September of 2017. So these missions, as I mentioned, often last far longer than they're actually originally slated for. This is very common. Hubble's another great example. Hubble has lasted decades longer than it was originally supposed to. The grand finale happened because the spacecraft, which at this point was so far past its original mission goal, was almost out of rocket fuel. So with these missions, we load them up with an amount of rocket fuel that's not crazy, it's just enough to sort of make corrections and adjustments in the orbit. If it's not facing the right way, if it's not quite in the right orbit we want it to be, we can remotely from Earth kind of shift it around, and that helps us study exactly what we need to study. So this probe was running low on its rocket fuel, so there's a meeting that was had, and it was determined that the best thing it could do, the most useful end to its story, was to crash it into Saturn and to take as much data as it could for as long as it possibly could to gather as much information about the interior of Saturn that we could possibly get. So on this grand finale, this time, this orbit, this final orbit, Cassini plunged into the planet's atmosphere, sending science data for as long as its small thrusters could keep the spacecraft's antenna pointed at Earth. Soon after, Cassini burned up and disintegrated like a meteor. So, moment of silence for Cassini. Did some excellent work for us. Cassini also gave us some phenomenal information on Saturn, also had a full kit of instruments on board, and also sent back some beautiful images. It not only orbited in one direction, its orbit was actually changed many times, so we're able to get images like this top-down view of Saturn. In Saturn, when we are going sort of around our Earth orbit, we actually see Saturn at different inclinations. So sometimes it looks more like a CD, sort of head-on. Sometimes you can see more of the actual CD face. So it does vary, but this sort of top-down view is one that is especially stunning. We got a lot of ring detail, and this is when we started to bring that count of the moons up for Saturn, because we got more detail on what's going on inside here, and even the image I showed earlier, there's a big difference in quality here, and sort of what we can see with the rings.
We see a lot of things in color,
Yes.
but I assume that everything is really not in color. It's just star color.
So a lot of images you see of space actually have additional color added to them to bring out certain kinds of light that the human eye can't see. So yes and no.
So we add
So
it.
what we would see is in line with what our eyes see on Earth, but oftentimes the pictures we get back have been updated. We also got this very famous image of backlit Saturn. So this is Saturn sort of forming an eclipse, if you will. The sun is behind it, and we're getting this really beautiful backlit view of the rings and the planet itself. So, what we are going to do in just a minute is we're going to go outside and take a peek at these giants for ourselves. Jupiter and Saturn are both up in our night sky, and if you'll allow me, I'll quickly show you where exactly they are. So, what I have here is a program called Stellarium. Please hold for spinning wheel of death. This is a free program, so if you're interested in astronomy, I highly recommend it. I'm going to reboot it quickly. This is as I mentioned, a free program available online. Feel free to look it up. This is a fantastic software that essentially uses models to model the entire night sky. Not only can it tell where you are on Earth and adjust based off of your location, you can also put in different times. So when Lily and I were brainstorming this program, I was able to actually put in, okay, what's happening in November? What's in the sky? Where's it going to be? And we can kind of figure out what we can look at. So if anyone here is interested in doing some stargazing, I highly recommend a program like this. So I'm at Boston, and I'm looking at 7:50 p.m., so right place, right time. And I can see here Saturn nice and high in the sky. Over here, I can look at its altitude, it's about 35 degrees, so not too bad. And it's in about the south-southwest sky. So when I go outside, I can take a compass or, my phone and figure out where's south-southwest and use that to find Jupiter and Saturn. And they're very bright, so they're pretty easy to find. Now let's look for Jupiter. I'm just going to drag us around here. We've got some nice bright stars, the summer triangle, Deneb, Altair, and Vega, sort of on its last legs as we enter into the true fall. And Jupiter, nice and bright right over here. We've got the Pleiades above it, Uranus, invisible, but there. Fun that it's there. And some notable bright stars, Aldebaran, Capella, Betelgeuse. And this is Orion down here. So, Jupiter, also very visible in the east. So, folks, what we are going to do now, I have my telescope in the back. I'll be bringing it out with us. It'll take me a couple minutes to set it up, but hopefully not too long. We're going to be heading out to the side yard, which if my directions is correct is this way? Yeah, right out this way. We'll take a look at Jupiter first, and then we'll probably have to adjust our position slightly to take a peek at Saturn. But I also think we have some folks who've brought other telescopes, which would be super helpful, amazing. So we'll have a couple of different scopes to show you guys these gas giants.
Can I just ask you a quick question?
Yeah.
Why do you think it is that Earth was the only one of the planets that developed such that it could sustain life?
Great question. There's a very clear band, if you will, of space around a star where you can have liquid water and oxygen and enough warmth to sustain what we know of as life. So it's just that it happened to form in that band. Mars, we think, might actually be in the band and is just a little too small to have made it this far. Venus is outside the band, which is why it's so hot and can't sustain life. So it's just being in exactly the right place at exactly the right time. Good question. All right, folks, with that, I'm going to go ahead and get my telescope and head outside. Thank you all for your attention.